Here we have the model that we developed using a multiplicative random walk for the SPY futures prices for 5 months forward, developed with the historical data series. Now we're going to use a different model to model the same time series, and that is the geometric Brownian motion model. The geometric Brownian motion model will be based on the additive returns, and the additive returns are the natural log of the ratio of the current price to the previous price. So we'll copy this additive return down for the remainder of the asset prices. We'll calculate the mean and the standard deviation of these additive returns. And the standard deviation, we'll use the stdev.s function in Excel. Alright, so we want to use this to simulate the asset prices. The parameters for geometric Brownian motion are based on the mean and the standard deviation of the additive returns. So this is the geometric Brownian motion formula, and the parameters required are mu, the rate of return parameter, and sigma, the volatility parameter. We estimate those using these formulas here that are based on the mean of the additive returns and the standard deviation of the additive returns. So we'll enter the Excel versions of these functions. Delta is 1/12 in this case because we are using monthly data to estimate these parameters. So mu hat is the mean of the additive return divided by delta plus the standard deviation squared of the additive returns divided by 2 times delta. So that is the estimate mu hat of the rate of return parameter. Sigma hat, the estimate of the volatility parameter, is sigma divided by the square root of delta. So the standard deviation of the sample additive returns divided by the square root of delta. So we'll estimate the price for these same days. Now, the random variable that's required in geometric Brownian motion is denoted by this z in the formula, and it is a standard normal random variable. So we'll enter a distribution that is a normal random variable with mean 0 and standard deviation 1. So we'll change this default 10 to a 1 and click OK. Now, because that just has numbers in here, this can be copied down. And so that's the random distributions needed to simulate geometric Brownian motion. Now we need to enter the geometric Brownian motion formula. We'll start with the same August stock price. And it'll be the prior price times the exponential function would be mu hat and we'll use absolute references on all these parameters, minus sigma hat, which is an H167, squared, divided by 2, and then times delta. Then we add to that sigma hat, which is an H167. I'm having to use the arrow keys to get to some of these cells that were behind my function there, and so it's possible you could put these in a different spot in the worksheet if you don't like to do that. And so that's the volatility parameter, sigma hat, times the square root of delta, times the standard normal random variable. And I won't enter an absolute reference on that standard normal random variable because I want to reference the different ones by month as we copy this down. Now we'll make this output here for the January 1st SPY price with the geometric Brownian motion. Okay, so we'll simulate both of these outputs for 1,000 iterations. And when we do this, we should notice that the mean is close to 133. The standard deviation is close to 11.5, and that's for the SPY with the geometric Brownian motion. If we click on the other output, well, we're close to 133 and close to 11.5. So these distributions are very similar, and if we simulated enough, they would become almost identical. We can see this if we use an overlay chart, and that's this chart here. Add overlay. And we'll overlay this output, enter a comma, and then the GBM output. And so now we can really see these two distributions that are very, very close together for the two outputs.